Assalamualaikum warahmatullahi wabarakatuh. Okay, today I will start some discussion for introduction of power quality for you. Okay, this video is made for my student in University Malaysia Pahang for power quality courses. Okay, so let's start. Okay, power quality is about economic value. Okay, this is our main motivation for learning power quality. Why? Because modern loads are more sensitive towards power quality. Okay, our factories, um, chemical plant, automotive industries, all has been integrated. The manufacturing process, the control process, all integrated and have a lot of relays, computer control relays, circuit breaker. So this is all integrated that makes if have a risk of if one circuit breaker fail, then the whole production stops, and that's costs a lot of money. Okay, these are some study by Georgia Power. I take this study from our Dugan Power Quality book. Okay, when they ask customer and utility, for example, yeah, in Peninsular Malaysia, TMB is a power utility. Okay, but of course, this study is not for TMB. So when they ask utility and customer, what are the costs? Who is responsible for power quality event? Both sides agree quite the same amount that natural disaster, natural causes like animals, lightning, that are the main causes for power quality problem. But the there's a lot of difference between the perception on their own responsibility towards power quality. Customer only say 12% of the problem comes from customer, while utility is 70%. While utility said their parts only contribute only 1%, while customer contribute 25%. Okay, so this is sort of disagreement between utility and customer, and that's where a power quality study is needed. Okay, the person who study power quality engineer is the one that can troubleshoot this up to the root cause to say that who is the responsible for the power quality problems. So let's talk about power quality. What is power quality? Okay, it's a matter of how reliable is our electricity. Okay, for example, at our house, we got 230 volt, 50 hertz. Do we get that all the time? If you have typical loads like household loads, you might not notice if the power goes down, not 230 but 200 volt. You might not notice. Okay, but sensitive equipment at hospitals, at manufacturing plant, they will notice this. Okay, so what are the effect of unstable electricity? There's a lot of effect. When we have a lot of sensitive load, okay, there's a lot of effects. Depends on how we tackle the problem. If we install good quality relay up to the standard, then we should not have any problem whenever typical power quality problem happen. Okay, let's say the event goes up, go down like up to 0.8 pu, but only for like 50 millisecond. That shouldn't be any problem if the relay is good enough, if our setting is good enough. Okay, another question is it about the quality of voltage or quality of current? Although power means voltage times current, but when we talk about power quality, normally we talk about the voltage. Why? Because the voltage is the one that been given to us by utility. Okay, so utility provide voltage. The client is the one that draw the current. Okay, so in short, according to a Dugan book, power quality is any power problem manifested in voltage, current, or frequency deviation that results in failure or misoperation of customer equipment. Okay, one thing about this definition is whenever there's a power quality event, okay, let's say the voltage drop down, but nothing happened on the customer side, production runs as usual, that is not constitute as power quality problem. Okay, so whenever there are problem like losses, then become power quality problem. If not, then it's okay. Why? Because there's an agreement between the utility and the customer. Okay, this is just an analogy of the agreement. Of course, the agreement is much longer than this. There's a lot of standards, but this is just a typical saying of what the agreement might look like. Okay, let's say the electricity provider said, okay, I will provide high quality electricity at a certain price. Okay, it will be 230 all the time. Okay, there are times that power quality happen, it goes below than 0.9 pu, but I promise that it will not last longer than 200 millisecond. Okay, and the customer side agree with that. Okay, that means customer need to install loads in the site that can handle this 200 millisecond below than 0.9 pu. Okay, we will talk about this more about what's the agreement. Okay, there are some standard that need to be um, abide by both party. Okay, typical power quality phenomena. There's a lot of power quality phenomena. In the last revision of standard IEEE 1159, they add a few more, but we will not discuss all of them. Okay, I'll show you what we discuss. Okay, first, the transients. Okay, there's two types of transients: impulsive transient and oscillatory transient. Okay, impulsive transient only goes to the one side, either on the positive side or negative side. Oscillatory transient, they're ringing, okay, oscillating. That's why it's called oscillatory transient. So normally for impulsive transient is very big. For this example, from lightning stroke up to more than 20 kiloampere, okay, but very short time, okay, in microsecond. While oscillatory transient, this specific example is because of capacitor switching. So whenever we switch capacitor bank, we will have this kind of waveform. Okay, so it's oscillate. And one of the parameter of this oscillatory transient is the frequency of the oscillation itself. Okay, sag. This is the most discussed power quality problem. Okay, because sag happen every day, and it constitute maybe 70 to 80% of power quality problem worldwide. Another name of for sag is D, okay, voltage dip or power dip. Okay, how does it look like? We want voltage like this. Okay, I'll show you. Okay, this is what we want. Okay, this is example for single phase. 230 volt, so the peak goes around 325 volt, and it's oscillating at 50 hertz, okay, to 20 millisecond for one period. It looks like this. It should be like this all day, all time. But sometimes will go down to become smaller amplitude like this. Okay, so how do we calculate this? This voltage sag, will be defined by two characteristics: the magnitude and the duration. So for this waveform, the magnitude, we will have to take this time varying waveform to get the RMS of it. Okay, so when you get RMS, it looks like this. It's slightly more than 50 volt RMS for this waveform, and then we divide that RMS by the nominal voltage in Malaysia, 230 volt. So when this 50 something divide by 230 volt, we will get 0.25 pu. Pu is per unit, and this is how we categorize this. So this waveform is at 0.25 pu magnitude. Another term is the duration, how long this event lasts. So it starts at 40 milliseconds and it ends at 160 milliseconds. 160 minus 40, we get 120 milliseconds. So this example, this specific waveform is 0.25 pu at 120 milliseconds. Okay, but voltage sag have a lot of range. Okay, anything from 0.1 pu to 0.9 pu, and the duration from half cycle means 10 milliseconds in Malaysia, up to 1 minute, that considered as voltage sag. Okay, and it happens a lot. Whenever you drive around, you see like trees, branches of tree touching the wire, or squirrel climb up pole. It might lead to power dip, voltage sag problem. Okay. Another thing is swell. Okay. Sag is when the voltage get lower. Swell is when the voltage got bigger. Okay. So this is typical swell. In this case, it's 1.2 pu. Okay. And the duration is 360 milliseconds. Okay, and swell goes from 1.1 to 1.8 pu, and the duration range is similar to voltage sag, half cycle to 1 minute. Interruption is different from voltage sag. Voltage sag from 0.1 to 0.9, but when it goes below than 0.1, this is what we call interruption. Okay, you might experience this. Okay, you call this event as blackout. Okay, but that's not the term that we will use in this course. It's called interruption. Power interruption. Normally, all electric loads will fail in this kind of problem. Okay, unless you got backup like UPS. Okay, so this typical interruption is at 0.02 pu and at 440 milliseconds. Okay, duration can last for half cycle to 1 minute as well, and at 0 to 0.1 pu. Okay, these three, sag, swell, and interruption, it goes under the category of short-term voltage variation. Okay, there are another category, long-term voltage variation. The first one in long-term voltage variation is undervoltage. Okay, when we say long-term in power quality, it means the event lasts longer than 1 minute. For this example, it starts from something from 1 o'clock to like 4 minutes. Okay, at 0.7 pu. The voltage goes down until 0.7 pu. Okay, this is the thing about power quality. When we say magnitude, we are not discussing about how much it lost, how much the voltage goes down. No, we're talking about the remaining voltage. In this case, the remaining voltage is 0.7 pu. Always talk about remaining, not how many percent voltage drop. Okay, so the remaining voltage is 0.7 pu and it lasts for 4 minutes. This is considered as undervoltage because undervoltage is from 0.1 to 0.9 pu when the duration is more than 1 minute. Overvoltage, normally from 1.1 pu up to 1.2 pu. Okay, so this is what it looks like if it's 1.2 pu and the duration is for 1 minute. Okay, and this is typical thing that you call as blackout, but it lasts longer than 1 minute. Okay, for this example, slightly more than 1 o'clock and it finished at 4:30. Okay, so it's 3 hours and 6 minutes at 0 pu. Okay, no voltage at all. And this is the typical magnitude 0 to 0.1 when the duration is more than 1 minute. That's sustained interruption. Okay, so we finished about event-based phenomena. Okay, there will be another steady state phenomena. This is not based on event. Okay, that we call as harmonics. Harmonics cause distortion. Okay, when we talk about typical electricity waveform, normally it looks sinusoidal. Okay, but when distortion happens, it doesn't look sinusoidal anymore. This is not sinusoidal. Okay, because why? Because this has harmonics. This is typical diode rectifier loads. When you charge your handphone, for example, your handphone might exhibit current loops like this. Okay, so this is how the current looks like, and this is what we call as harmonics. Okay, we will touch about harmonics later. Okay, our main reference for power quality phenomena is IEEE 1159. Okay, you have to download this. Okay, if you inside UMP, you can just go to IEEE website and download IEEE 1159. If you are outside of UMP because of this pandemic, you need to go to library easy proxy, then you can download this standard from IEEE website. Okay, like I said, there's a lot of categories for power quality phenomena. We will not touch all of them. What we will touch is transient, short duration RMS variation, long duration RMS variation. This is for the event-based power quality problem. And for steady state, this is all steady state. We will touch only on the harmonics. Okay, because we need to define our boundary for learning. This is only 3 credits course, so we will touch harmonics. And that's all for introduction for power quality. Oh, I forgot one thing. All these power quality phenomena that we have discussed, the range of magnitude is below 0.9 or it's more than 1.1 pu. What's in the middle of that? From 0.9 to 1.1. What do we call voltage if it's sit in that tolerance 0.9 to 1.1? We call that as normal operating voltage or nominal voltage. and if it sit in that one, it should be no problem. Okay, remember this agreement I put here. 230 volt all the time with 10% tolerance. Okay, this 10% tolerance is what the agreement from the provider, electricity provider, for power quality from 0.9 to 1.1. That's 10% tolerance. Okay, so you know how to extract information of magnitude and duration from waveform. Okay, I will set up a quiz in Column to test your knowledge in extracting this information and to classify one waveform is belong to what type of power quality phenomena. Okay, refer IEEE 1159. Okay, especially table 2. Then we will do the quiz, and let's say how you able to extract the information and categorize power quality event. Okay, that's all for today. Take care. Bye. Assalamualaikum warahmatullahi wabarakatuh. Thank you.